All right, so we're looking at our spring example, so let's go ahead and take a look at this question. An unstretched spring is 12 centimeters long. Okay, so I have an unstretched spring that is 12 centimeters long. Okay, that is 0.12 meters. Quick trip math there. Part A says, when you hang an 875 gram weight from it, it stretches to a length of 14.4 centimeters. What is the force constant in newtons per meter of this spring? Okay, so they put on a 875 gram weight, and it now stretched to 14.4 centimeters, meaning that it stretched how far? Well, it stretched 2.4 centimeters. Well, that's 0.024 meters. And so whenever we do these problems with springs, it's kind of like we did with friction. We're going to draw our free body diagrams, we're going to put in this elastic force, and then we're going to substitute in. Well, that elastic force is made up of the spring constant, or the force constant, and how far has it been stretched from its equilibrium, or its unstretched length. And so in this case, our x value is that 2.4 centimeters, or that 0.024 meters. So let's go ahead, draw our free body diagram. We will have to convert grams into kilograms here when we do this problem. So let's go ahead and set up our equation here. So I drew my free body diagram. The spring's pulling it up, gravity's pulling it down, and so I'm left with the sum of the forces in the y direction equals 0. So it's come to a new equilibrium point, if you will. And so the acceleration is 0 at this point. So I have Fe minus mg equals 0, and we're trying to find this spring constant. So that's inside that Fe. So I have Kx is equal to mg, so we'll move that m over to the other side. And I want to find k, so I just have to divide that x. So I have mg divided by x. Plug in my numbers, so 0.875 kilograms times 9.8, that will give me the newtons on top, divided by my 0.024 meters. And I get a spring constant here of 357 newtons per meter. Now this is the spring constant, meaning as long as we're inside that range that follows Hooke's law, that value will be constant. So if I stretch it, in a reasonable range, we should be okay. Again, we want to remember to stay in that range. If we get outside that range, Hooke's law doesn't apply, and we would be committing spring abuse. We do not want to do that. All right. So the next part B says, all right, what total mass must you hang on the spring to stretch it to a total length of 17.72 centimeters? Okay, so now we're going all the way to 17.72 centimeters. So how far have we actually stretched it? Well, it originally was 12, so we have now stretched it 5.72 centimeters, or 0.0572 meters. So we've stretched it a new length, and we want to know what is that mass we hung on there. We want to know what m is. All right. So again, we set up our free body diagram, we generate our equation, and we solve. So I set it up. The sum of the forces of y is equal to 0, and I have Fe in the positive, mg in the negative, and I'm trying to find this mass. I have that Fe, but I need to substitute, just like we did with friction before. So I have Kx minus mg equals 0. Now I know the x value is 0.0572. I know g. I'm trying to find m. So the spring constant, because it's called the spring constant or the force constant, it's the same in all of these situations, assuming we're in that acceptable range. So I'm solving for m. So I got Kx equals mg. Divide the g over, so I have Kx divided by g equals m. Plug in my 357.3 number. If it was anything extra, I'd probably stored it on my calculator, times the x of 0.0572 divided by 9.8 will give me my mass. And you should get a mass value here of 2.09 kilograms. And there's our example.